now we move to the application of Gauss law to find the electric field. This is actually the reason behind studying Gauss law in this course. We will see how we can apply Gauss law to find the electric field of charge distributions when we have high symmetry of the charge distribution. We will first state the strategies and explain why this is the strategy that one should follow in order to apply Gauss law, and then we will consider specific examples with charge distributions having various symmetries. Now, the most important point is to take advantage of the symmetry of the Gauss of the charge distribution that is given, so that you can pick up a Gaussian surface. Remember, when you want to apply Gauss law, you need a Gaussian surface, and then once you have this Gaussian surface, you have a relation between the flux through this surface and the charge enclosed by this surface. So the first thing is look at the symmetry and pick up a suitable Gaussian surface. A convenient Gaussian surface will make your life easier. Now, how you pick up this Gaussian surface depending on the symmetry? The first thing, usually when you have a charge distribution, you are requested to find the electric field at some point. That Gaussian surface should pass through that point, because otherwise there is no point in choosing this surface. The second thing is you must have the electric field constant, the magnitude of the electric field constant throughout the surface, or at least part of the surface. Sometimes you need to pick up out a surface which is composed of different portions. For example, a cylinder which has cylindrical part and the top and the base. Okay, at least it should be constant. The electric field should be constant through part or portion of that surface. For example, the cylindrical part of the cylinder. The third thing is that you concerns the direction of the electric field. You know, in the Gaussian integral, the flux integral that appears in Gauss law, there is this E dot dA term, E dot dA. Now, you should choose your Gaussian surface so that your electric field on the surface, or at least portions of the surface, is parallel to all dAs on that surface, or portion of that surface. Why is this? In this case, this E dot dA will reduce to E dA. There will be no cosine theta to worry about. Okay, so cosine theta in this case will be just cosine 0, and it will be 1. Or sometimes you need to take it antiparallel, or at some part of the surface you might take E and dA perpendicular, so that you know that there is no flux through that part of the surface. Eventually, as we go on, we will encounter these situations, and we will see how all these are fulfilled by our choice of the proper Gaussian surface. Of course, choosing a right Gaussian surface is a matter of experience, and we will highlight the application of Gauss law to different symmetrical charge distribution, different symmetries of the charge distribution, like on a line, on a plane, on a sphere, where you will get some experience, and you will also need to try to do some exercises yourself to see how you can apply these. I mean, it takes you to do hands-on in order to be able to master the topic, and it is easy once you master it, by the way. So why are these three steps important in choosing the Gaussian surface? Because the strategy is the following. Now, this is the remember, our aim here is to find the electric field of that charge distribution using Gauss law, not to calculate the flux. The flux we already know. Just count the charge inside the surface, and we'll find the flux. We want to find the electric field. So what you do in this case, so why you choose the electric field to be uniform, and why it is parallel, or at least anti-parallel to dA? Because on the left-hand side of Gauss law, you have this integral. On the right hand side, you have this integral. This is Gauss law. It says this integral is equal to this value. Now, if you choose your Gaussian surface so that E is parallel to dA, then E dot dA reduces to E dA. Okay? For all dA. This means that the electric field should be parallel to the normal at all throughout the whole surface. If this happens, then in this case E dot dA reduces to modulus dA multiplied by 1, which is cosine 0, okay, when they are parallel. And when the electric field's magnitude is constant at the surface, then that field is constant. You can take it outside the integral. So this reduces to this very simple expression where the E at the surface is now constant and it is outside the surface. So you end up with E multiplying this expression. What is this expression? It is the integral over the area elements, the magnitude of the area elements, calculated over the whole closed surface. But what is this? We have seen that. This is just the area of the surface. So the left-hand side of Gauss law reduces to the electric field at the surface multiplied by the area. And therefore, if you divide now by the area, then you get your electric field equal charge enclosed by the surface divided by the area multiplied by epsilon naught. So you have found the electric field at the surface. But you know, you have chosen your surface to pass through the point where you want to find the electric field. And therefore, finding the electric field at the surface means finding the field at the point where you were requested to find it. Okay? So that's what happens. Of course, there is an A missing here. When you divide by A, an A must appear here. So the field will be E equals Q enclosed divided by A over epsilon naught. Once you have done this, what remains is to figure out what is the charge enclosed by the Gaussian surface. Okay? Sometimes even figuring this charge might not be a trivial job. You have to be a bit careful. Okay? So this is the general strategy of applying Gauss law. And as you can see, the idea is that make use of the symmetry so that you do not need to integrate this complicated integral. So that's the idea. So although Gauss law looks a bit scary and with this integral appearing here, but actually it is utilized, its utilization is actually in not doing the integral in order to find the electric field. If the charge distribution does not have sufficient symmetry, so that you cannot find such a Gaussian surface that enables you to do what we have said, then in this case the Gauss law is not the correct tool for finding the electric field. You have to do it by integration as we have learned. Let's consider a specific example in this case and see how we can apply what we have just said and apply our strategies in this case. Our example is a solid sphere which carries a total charge Q, and this charge Q is uniformly distributed over its volume so that it has a constant charged volume charge density rho. What does this mean? Think of you have a powder and you bring charge, spread it through this powder and uniformly. Then you wet this powder and you make it a dough, and then you construct a sphere out of this dough. In this case, the charge has been spread over the whole material of the sphere uniformly. Okay, has been distributed uniformly, evenly. Now, the per volume, the charge per unit volume in this case will be, which we denote by rho, is just Q divided by the volume of the sphere. This sphere of charge has a volume, has a radius A, so its volume is just 4/3 pi multiplied by A cubed. This is the volume of the sphere. Okay, so rho in this case is just a constant, and we know it. Now, we are requested to find the electric field due to this charge distribution. First, at points R outside the sphere. We measure R from the center of the sphere, and if R is greater than A, then it is at any point outside the sphere at a distance R from the center of the sphere, where R is greater than the radius of the sphere. Okay, so this is the point that we need to find the, it's an arbitrary point, because usually when you want to find the electric field, you want to find an expression for the electric field in this space. So here, this expression that you will find will be valid for any r outside the sphere. This is what is requested. Now, for this purpose, you first choose your Gaussian surface. That should be a surface that passes through that point r. So choose any point here, and the surface should be passing through that point. The second thing is you have to choose what should be that Gaussian surface. Okay? Again, it's a hypothetical surface that you create mentally and you imagine that exists here. Okay? It doesn't need to coincide with any physical surface that exists. It doesn't have to do. It has nothing to do with the surface of the sphere, of the spherical charge distribution. So how do we know it? I look at I want this Gaussian surface so that, to choose this Gaussian surface, so that the electric field is preferably constant and parallel to the dAs if possible. Now, from the symmetry of the charge distribution, because it's uniformly distributed over this volume, I know that if I consider a sphere, a spherical surface, that is centered at the charge distribution, then as I move along this spherical surface and look at the charge, I always see the same charge environment, because the charge is uniformly distributed, from all points on the surface. You can agree on that. It is like if you think of this as a hot object, and the heat is distributed uniformly over the sphere itself, then when you go around the surface centered at the sphere, you will feel the same heat wherever you go. Okay? In our case, it is charge. So when you go on a surface, we move along the surface of a sphere centered at this charge, and you look at the charge distribution, the environment that you see, because of the even distribution of the charge, is actually the same. Okay? The meaning of this, since the charge environment is the same, the electric field generated by this charge distribution must be the same at all points, as far as magnitude, must be the same at all points on the surface of the sphere. So this is number one. That is, at the surface of the sphere, we have a field that has a constant magnitude when we pick up a sphere. What about the direction of the field? Well, again, due to symmetry, the electric field here will be directed radially outward. In other words, it will be along a ray coming from the center to the point. That's along radius. And if this charge is positive, it will be radially outward. Now, why is this? Again, because due to the symmetry and the fact that the charge is evenly distributed, you can, and this electric field here is generated from all portions of the charge. If you think of the charge here distributed uniformly over the volume here as being composed of small dq's, and if you divide this into small dq's, you can just by doing small thinking, a bit of thinking, you can see that when you add up the contribution of all these dq's at this point here to find the electric field, the components that are not radial will cancel each other, and you will get only radial field. Okay? And this applies to all points on the surface of the sphere. So now the field is radially outward if the charge is positive, okay? Which means the field is proportional to dA vector. Okay? The dA vector, because the dA vector is the normal to the surface and it's pointing outwards. Okay? So this is what we have in this case, and therefore we have fulfilled requirement 2, which is the field is parallel to the dAs at all points on the surface. Now, having done this, things become very easy. So E dot dA therefore reduces to EdA, because E is parallel to dA all the time. Cosine theta in this case is cosine 0 for all dAs on the surface, and it reduces to this. Now, the right-hand side of Gauss law, what is it? It's Q enclosed divided by epsilon naught. What is Q enclosed in this case? Before I go further, Q enclosed is the charge enclosed within the Gaussian surface. This Gaussian surface encloses the whole sphere. The charge on the whole sphere is just capital Q, so it's capital Q over epsilon naught. Now, so this is what we have. Now, the next step is, as you might appreciate, is just observing that E on the surface is constant, as we have just argued, and so it can be taken outside the integral. You can see here. And what remains is calculating this, which is the area of the sphere, which is 4 pi r square. So E multiplied 4 pi r square is equal Q, the charge of the sphere, divided by epsilon naught. And if you write it this way, E is equal Q over 4 pi r square epsilon naught. Now 1 over 4 pi epsilon naught is K, that appears the Coulomb's constant, and so the electric field at the surface, the Gaussian surface, is this. Okay. Now it's directed radially outwards. So for the meaning of this is that at any point at a distance r from the center of the sphere, because this is valid for any r, we did not specify for a specific r. The only condition was that r is greater than a. Okay, that we are outside the charge distribution, is just this, and it's directed radially outward if the charge is positive. Evidently, if the charge is negative, it will be directed radially inward. That's the only difference. So this is our expression. Now this is something quite remarkable, because this looks like what? Looks like the electric field of a point charge of magnitude capital Q centered at the origin. Now this is part of something called the shell theorem. The shell theorem usually states that for any spherically symmetrical charge distribution, regardless of any other consideration, the electric field outside that charge distribution is that of a point charge whose magnitude is equal to the spherical charge distribution centered at the center of that charged distribution. Okay, so this is our result. And as you can see, it's very easy. Once you make the correct choice of the Gaussian surface, life is very easy, and you don't do any integrals. Now, let's look now at another area, which is R inside the surface. You want to find the electric field inside the surface. That is, at points R away from the center, but so that R is less than A. Okay, so you are inside the surface. Now, again, we want to apply Gauss law and try to follow the same algorithm that we have. First of all, however, before that, what will be our Gaussian surface? Again, if you consider a spherical surface, spherical Gaussian surface, hypothetical surface that you imagine or draw yourself here, which is at a distance r from the center. If you imagine this surface or draw this surface, and you move on this surface, you will always see the same charge environment. Whether it's from in or out, doesn't make difference, but you will always see the same charge environment. This tells you that the electric field magnitude is uniform over this surface. Again, due to the symmetry, you can see that all the you will have only radial component of that electric field. Okay, so which is normal to the surface. Try to do some thinking, and you will come to this result also. So these two arguments are important, and this tells you that, again, a sphere is actually the right Gaussian surface to pick up. So once I choose a sphere, this sphere, which has a radius now less than a, and it's inside the spherical charge distribution, I can apply Gauss law and try to find E. Now, in applying Gauss law, you need Q enclosed. The right-hand side of Gauss law is Q enclosed. Q enclosed is the charge enclosed by the Gaussian surface. Now, here you have to be a bit careful. Because this surface is within the charge distribution, it doesn't enclose all the charge capital Q. Okay? It encloses only this part of the charge. This part is not enclosed. So what is the magnitude of this charge enclosed? Well, if you know the charge density, because the charge is uniformly distributed, then if you know this volume of this sphere, which has radius small r now, not a, multiply this volume by rho, the charge density, then you find what is the charge enclosed by this Gaussian surface, which is this. Okay? Now, apply Gauss law. Again, the integral E dot dA reduces to this because the electric field is radial and parallel to dA, and you can take A outside the E outside the integral. This is integral over dA. Now, the area is 4 pi r square, and this is equal Q enclosed over epsilon naught. Substitute for Q enclosed here and do some algebra, and you get this expression. So E inside at a distance r from the center is equal to a constant, which is rho divided by 3 epsilon naught, multiplied by r. So it is a linear function of r. Okay, it's constant multiplied by r. So the field from the center then is 0, and it grows linearly as you go out. Okay, and it's radial. At each point is radial. So we have found actually what is the electric field now inside the sphere and outside the sphere. Okay, you can express rho in terms of the total charge divided by the volume of the charge distribution. Okay, this is just what I have said at the beginning of the discussion of this chapter. Because what is rho? Rho is the charge density. The charge density is the total charge of the charge distribution divided by the volume over which this charge is distributed, which is the whole volume of the sphere. Okay, because the charge distribution is distributed, the charge distributed over the whole volume. So this is your Q, your rho, and if you do it this way, you get this expression. Note this is not equal to the electric field of a point charge. So because now shell theorem doesn't apply here, because shell theorem applies to the cases when you want to find the electric field outside the charge distribution. Here, the electric field is to be found inside the charge distribution. Now we can plot actually the electric field here as a function of r. So this is the chart. So in this region, between when r goes from 0 to a, the electric field grows linearly. So it is 0 and then it grows linearly. Then after that, the electric field is kq over r square. It drops like 1 over r square. Now we have drawn the electric field to be continuous at the surface. Okay, the continuity of the electric field at surfaces is not always guaranteed. Actually, electrical engineers will learn probably more about this in their more advanced courses. And but let's check that in our case here it is, because take the electric field, for example, from the right. Okay, the electric field from the right, which is here to the right of the surface and outside the surface. If you take the limit when r approaches the surface, this is the value of the electric field. Now consider this expression, the electric field from the left, and take the limit when r approaches a. That's when you are on the surface. So this limit is straightforward. Just substitute a, and you get this expression. Note that they are the same. This tells you that the electric field is continuous at the surface, and so we were rightful in writing down the electric field as continuous. Okay? So the value that the electric field approaches from inside the surface and the value that it approaches from outside the surface is the same.